Hey folks, this is the second lesson in our unit on reaction rates and equilibrium, and in this lesson we're going to be focusing on that term equilibrium and what it means and what's going on when we've got equilibrium. So three main goals that we're going to talk about. First, we're going to actually talk about what equilibrium is, and if we could zoom way in on our molecules in equilibrium, figure out what exactly it is that they are doing in this state. Second, we'll start talking about how changing the amount of reactant will change the amount of product that's formed or vice versa. And then to delve a little deeper into that, we will talk a little bit about something called the Chatelier's principle and how that allows us to determine how changing factors will affect the equilibrium position, in other words, the ratio of reactants to products of a particular reaction. Now, in order to help us understand equilibrium, I present to you a tale of love and woe. Okay, this is Equilibrium Island. On this island, we have 20 single girls. Oh, look, they're cute. 10 single guys. Oh, so cute. And, oh my gosh, 10 couples. Oh, look at them. They're adorable. All right. Now, on Equilibrium Island, sometimes tragedy, a couple would split up. But then also, about as frequently, we would find new couples getting together and finding love. All right? So this was happening all the time. Couples would break up, other couples would get together, just in this sort of ongoing process, just like, hey, in real life. Now, here's where it gets interesting. One day, we had a shipwreck near Equilibrium Island. Oh no, the RV Palma, it's going down! Swim to safety! Ah, it's a shark! And death. Alright, so anyway, this ship that sank near Equilibrium Island was mysteriously carrying all men, for reasons unknown to any of us, but there were 105 guys that we have added to the island. Alright, now the question is, when we suddenly throw in an extra 105 single men, what's this going to do to our equilibrium situation here? How's that going to change the number of single guys we've got, the number of single girls, and the number of couples? Because we've had a pretty steady thing going for a while with 20 single girls, 10 single guys, and 10 couples approximately at any given time. But now that we've added all these extra guys, that's going to change the social dynamic of this island. Now, what you would probably expect if you just reason through this a little bit, and I know that you go to OSHA where the ratio is very dramatic, so you can easily imagine this. Adding 105 guys to this island will obviously increase the number of single men because there's a whole lot of them, right? This increase in the number of eligible young bachelors also means that we'll see an increase in the number of couples. Our single girls will have more options in the dating pool. Okay. What that also means then is that our number of single girls is going to go down because more of them are going to be able to find a potential sweetie pie. Okay. So a new equilibrium position that might be established might be that we only have 5 single girls at a time, whereas before we might have 20. This would leave 100 guys that are single and 25 couples. All right, so just by having this shipwreck of all these guys crashing next to the island, we've suddenly drastically changed the working social dynamic of our island. I know, it was a very riveting story. All right. Now, as cute and corny as this was, this actually does give us some useful insights into how reactions work, right? The first key point that we can take away from this is that reactions are reversible, okay? Once 2 people get together and form a couple, it's not like that's set in stone forever. People break up, all right? Sometimes as frequently as they get together. So the first idea is that when we get 2 reactants bonding together to form a product, they can split up again. It's not like they're stuck together forever, all right? The same as it is in, human relationships, okay? So when we mix 2 substances together to get some product, we're also going to have some of the product reverting back into the reactants again. We get both the forward reaction, which is going from left to right, but at the same time we also get the reverse reaction where our products are transforming back into the reactants again. They're both happening simultaneously. Right? Now, The good news is that even though we've got some forward reaction going and some reverse reaction going, and it's chaos, bonds are breaking, bonds are forming, new things are being created all the time, we do eventually, with any system, reach a balance. This sort of stable, steady ratio of reactants and products. Okay, so say for example we had a nice steady ratio where in a given group of people we typically have 5 single girls, 7 single guys, and 3 couples. Right? Now it's true on occasion we would get the reverse reaction occurring where we take one of those couples on the right hand side and break them up to become the reactants again. But we would expect with approximately equal frequency that our reactants would also be getting together to form new products, which allows these levels to stay pretty constant. Okay. Now we call this situation equilibrium, where we have pretty steady levels of all of our reactants and all of our products. We don't see big changes in the amount of each one that is being produced at any given time. Now some key things to know about equilibrium. First of all, equilibrium does not mean that things have stopped reacting. All right. Even though things look nice and calm, we're still getting reactions happening. Bonds are breaking, bonds are being formed. We still see things reacting. Okay. But even though there are reactions happening, we don't see a big change in the amount or concentration of reactants or products. Right? The reason for this is because the key defining feature of equilibrium is that the rate of the forward reaction is equal to the rate of the reverse reaction. Okay, so every time we get reactants forming a new product, at the same time there's another product that's reverting back into its reactants. So everything ends up canceling out really nicely. Now, if you see this graph in the upper right-hand corner, this was one in the previous lesson where we are graphing concentration of each of our products and reactants over time. And the point at which we reach equilibrium is when those levels kind of level out. The slope basically goes to 0. We don't see a big change in the concentration of products or of reactants. They're still reacting, there are still things changing, but in the end, overall, the levels stay about the same. All right, what we have down here is the same basic thing, except instead of looking at the concentration, we're looking at the rate of the reaction. Okay, we eventually hit a point where the rate of the forward reaction and the rate of the reverse reaction overlap each other. They intersect. So they reach the same level. That means equilibrium has occurred. All right. So that's the big first key idea for you to have is what it means to be at equilibrium and how that reflects on the equity basically between the rate of the forward reaction and the rate of the reverse reaction. The other thing that equilibrium island tells us is about that whole shipwreck thing, right? When we added a bunch of single guys to the island, that didn't just mean that we had more single guys. That ended up also causing everything else to change as well. Adding more single guys caused an increase in the number of couples and a decrease in the number of single girls. Okay? In other words, we can't just add one substance and not have everything else change along with it. Okay, because when we change the amount of one thing, that changes the whole dynamic and what reactants and products are available and what ratio is going to make the most sense for all of those different substances to assume. Okay, this is summed up in something called Le Chatelier's principle, okay, which states that if we take a system at equilibrium, so everything's nice and steady, forward and reverse reactions are going about the same at this point, and then we change the situation somehow, we add more of something, we change the conditions in some way, that's going to mess up our equilibrium, and our system is going to have to change a little bit, and those ratios of reactants to products is going to have to change to kind of offset that big imbalance that we've just experienced as a result of this stress on the system. Okay, now there are 4 main rules to keep track of in terms of predicting how a stress on the system is going to change the amount of reactant and product that we have. I'm going to go through these pretty quickly. We'll spend some more time in class delving into these a little bit deeper. Okay. Now the first rule has to do with the concentration. Okay. So this is very much like our equilibrium island example where we added more of one of our substances. So if we change the concentration of a substance, that's going to cause the system to shift. Okay? So if we increase the concentration on one side, that's going to cause more of the opposite side to be produced. Okay? To kind of highlight this a little bit more. When we saw an increase in the number of single guys, what that did was created more couples as a result of it. So by increasing the number of single guys, what we ended up finding is that the equilibrium position shifted so that we had more couples than we did before. Okay? It's the same basic idea with this first rule. So an increase in the concentration of something on one side will cause the reaction to shift so that we get more of the other side to kind of balance it out. Okay, and then vice versa, if we see a decrease on one side, then the equilibrium position will shift towards that side to kind of offset that lack of that particular substance. Okay. One thing to note is that this is only true for aqueous and gas substances. Changing the concentration or amount of either a liquid or a solid has no effect on the reaction equilibrium position whatsoever. Just a fun fact for you. All right. Now the second rule to consider has to do with pressure and volume. Okay. Now pressure and volume, as you might have figured out at this point, are mainly things that we're concerned about with gases. We don't really have to worry too much about pressure and volume changes affecting solids or liquids. It's really gases because they're the ones that can be compressed. Okay. So what we find is that when we increase the pressure or decrease the volume of the container that our system is in, our reaction will shift to favor whichever side, either reactants or products, has fewer moles of gas. So basically you could look at a reaction, count up all the moles of gas on each side, and whichever one is smaller, that's the side we're going to get more of when we increase the pressure or decrease the volume. If we do the opposite, we decrease the pressure or increase the volume, it goes the other way. It favors the side with more moles of gas. Third rule has to do with temperature. Okay. Now this is really only important when we're dealing with reactions that are either exothermic or endothermic. Because what we'll find is that, say for example, we increase the temperature, right? If there's one side of the reaction that creates heat, we're not going to want to go to that side of the reaction. So say for example, we have an exothermic process, so the more product we get, the more heat that's also produced as a byproduct. If we increase the temperature of the system, the last thing that our reactants want to do is create more heat to contribute to that. So what we'll find is that it'll shift over to the side that doesn't have heat as one of its substances on that side. Okay. I realize that was maybe kind of confusing, but we'll talk about it more in class. Right? And then the last rule, I think you're going to like this one. If you have a catalyst, it does nothing. All right, so adding a catalyst to a system has no effect on equilibrium position because it speeds up the forward reaction and the reverse reaction the exact same amount. So yeah, we have couples breaking up and getting back together faster and faster and faster, but in the end, they're both going faster, so everything ends up canceling out. All right. When we get together, we're going to spend more time looking at these ideas and how to predict what's going to happen to the equilibrium position as we introduce various stresses and kind of freak out our system. So, stay tuned. We'll have some fun.